Okay, Assalamualaikum and hello. Welcome to the Z1213 Instrument and Measurement online lecture course. Okay, this is a series of lecture. Uh, this series we will discuss on chapter 3, noise in measurement. Okay, for today lecture, this is the content that we will cover in this session. Objective of today lecture is for you to know what is measurement, what is noise. Okay, to know the source of measurement noise and then the techniques for reducing noise. Okay, so what is noise actually? In previous chapter, in chapter 2, we has already discussed and in detail analysis of error and the error of source that coming during the measurement process and during sensing the value of physical variable when generating an output. Okay, that we already cover. And then, however, but in this chapter, further error often created in measurement system when electrical signals from the measurement sensors and transducers are corrupted by some kind of induced noise. So, in general, noise comes both within the measurement circuit itself and also coming from during transmissions of the measurement signals to a certain point. Okay, so this noise usually comes from the measurement circuit itself or during the transmissions. So in this figure shows the effect noise has on an electrical signals. Okay, as you can see, the grassy looking swingles superimposed on the sine wave is actually an electrical noise. This noise contains a multitude of frequencies and amplitudes that can interfere with the quality of signals. So this is the signals that without noise, and this noise already disturb the actual signals. So the extent to which series mode noise corrupt measurement signal is measured by a quantity known as signal to noise ratio. Okay, so what is signal to noise ratio? Signal to noise ratio is defined as Sn, that usually measures in dB, is the log of signal power over noise power. Okay, it's the ratio between the signal power to the noise power measured in decibels. So for using, as you can see here, we have two equations for deriving signal to noise ratio, which is 20 log signals RMS and 10 log signal powers. When do you use 10 and when do you use 20? 10 is used when you are comparing the power of the signal output compared to the noise power. When you referring to the voltage RMS, then you need to use 20. Okay, so both the desired signals and the noise appears at the same point in the system are measured across the same impedance. Okay, so this is when we measure we verify the signal to the noise ratio SNR. Okay, so in case of alternate current noise voltage, the rule mean square value is used as the mean. Okay, so so we use this formula. Okay, so this is an example how to derive, how to calculate the signal to noise ratio. You can pause these slides in order for you to do some practice on yourself. Okay, so the question is asking you to determine the input to noise ratio. Okay, a non-ideal amplifier has an input signal power of 2.5 times 10 power of minus 10 watt, and the input power noise is 3 times 10 power of minus 18 watt. So determine the input signal noise to ratio. As in the previous slides, we have two equations to determine the signal to noise ratio. Okay, so you can practice, you can check back, revise back in previous slides, which is the correct question to use for this kind of problem. Okay, you may take your time to pause these slides to do the exercise. Okay, so here I show you the solutions to determine the signal to noise ratio. Okay, since that the magnitude of signal to the noise is measured in power, so we are using the formula signal to noise ratio equal to 10 log signal noise ratio. So do not use 20 as the pointed value is not RMS. Okay, it's not AC voltage RMS. So here we use 10 log, and then we apply into the formula, and we will get 79.2 decibel. So this is how much noise ratio to the signal power. Okay. So noise actually can be generated from sources that are from internal and external measurement system. Okay, so there are two kind of noise source, that is coming from internal noise or from external noise. Okay, what is in internal noise? Internal noise is causing from internal device or components that comes from the circuit itself. So a form of internal noise is actually present only when there is a signals. So when you turn off your signals, automatically the noise will also zero. So no signals, so no noise. So this is internal noise. And then for external noise is a noise that generated source that outside of the electrical circuits. For examples, we have atmospheric noise, solar noise, cosmic noise, and man-made noise. Okay, for atmospheric noise, it is caused by lightning discharge in the thunderstorm, and also other natural electric disturbance occurs in the atmosphere that will lead into noise into your measurement systems. For solar noise is a normal condition. There is a constant noise radiation from the sun. It is simply because a large body at a very high frequency radiates over a broad frequency of spectrum. This also will, in a results, give you a certain amount of noise towards your system. So usually in the another example of for external noise is cosmic noise. Okay, so when do we see solar noise or cosmic noise? Is some things that measure in the outer space. For example, in your satellites, in your ISS, okay? So this measurement system do have this kind of noise. So for example, cosmic noise is coming from star that radiates RF noise in the same manner of the sun, this one. Solar noise also, this also cosmic noise is coming from the other sun, okay? Stars. Because our sun is also star, so solar noise coming from our sun, and then cosmic noise coming from other solar system, from other stars. Okay. So as I said earlier, noise can be generated from both external and internal source. It will disturb your measurement system. For internal source includes thermoelectric potentials, short noise, potential due to an inductive coupling, capacitive coupling. Okay, so this kind of noise is coming from uh, internal source. Okay, we will discuss further all this kind of source of noise in later slides. Okay. So inductive coupling. So the primary mechanism by which external device such as a main cable, okay, and equipment, for example, your fluorescent lamp and circuit operating at audio or radio frequency can generate noise through inductive coupling. Okay, so if signal carrying cable, for example, this one, if a signal carrying cables are close to such an external cable, a significant mutual inductance can exist between them. Okay, so as shown in figure, this we consider we have two parallel of electrical wire cables. Okay, these main cables is for example will give you an mutual inductive to another system. Okay, inductive from inductive generate from this inductive mutual inductance, it can generate a series of mode noise. This one Vn voltage, mode noise voltage. This mode node voltage is generated a small volume, several millivolts, okay, given by a formula of Vn equal to Mi. M is the mutual inductance, I is the current from this main circuit. So this distortion or noise Vn plus the Vs, you get the output signal. So this output signals is actually already added with some noise coming from the inductive coupling. Okay. So when these two cables are near enough, it will generate a mutual inductance. Okay, so this will give you some noise to your measurement system. Okay. So for another sample of noise coupling, we have capacitive coupling. Okay, so capacitive coupling compared to inductive coupling, they have some close relations. It is due to the arrangements of the wires that are very close. Okay, so for capacitive coupling, also known as electrostatic coupling, occurs between signal wires in a measurement circuit and a nearby carrying conductor. Okay, main cables. For inductive coupling, okay, your cables is active. It has a current flow. Now for capacitive coupling, your signal source having voltage and current flowing in your circuit. Okay, these main cables no circuit flow, no current flowing, and earth no current flowing. Okay, so okay, so this example, this figure shows example how the capacitive coupling occurs when your signal or measuring instrument circuit is very close to a certain conductor. Okay, so these cables, although not flowing currents, this is a conductor, and then when it is close enough to your circuit, measurement circuit, it will create a conductor. This one, C1, C2, and C3. Okay, so the magnitude of the capacitance between each signal wire and the main conductor, for example, in this figure, okay, C1 and C2, okay, to the main cable, this one, although it's non-active, it will create a conductive, a capacitance, okay. So C1 and C2, and then another one is your measurement circuits wire compared to the earth ground, it will create another capacitance. So bear in mind, this capacitance is not connected, but it will create a capacitive coupling. Okay, so usually in ideal way, okay, the capacitive coupling is usually 0. Okay, because C1 is equal to C2. How it is equal C1 to C2? Because this C1, the capacitive coupling of C1 and C2, since that the here is equal, okay? So it is balanced. So this actually is equal to 0 lah, actually, okay? Because the distance is equal. For capacitance calculation is V equal to C and then dV. Okay, so since that the distance is equal, is actually equal to 0 in ideal way. Okay, same as the capacitive coupling between ground and your cable is actually C3 and C4 is actually equal to 0. However, exact balance is unlikely in practice because wires are not perfectly straight. So if the wire is not perfectly straight, it will cause a distance, a different distance between this wire and another wire. So when there is a difference, so there is a difference in capacitive. When there is a capacitance difference, there will be a small portion, it will generate a small value of voltage noise, mode voltage noise due to the capacitive coupling. So the actual signal source will be distorted by having this effect of capacitive coupling. Okay. So this is the source of noise that coming from capacitive coupling. Okay. So there's some series mode noise voltage induced by capacitive coupling. We can call it's actually exists, although in small value. Okay. Another source of measurement noise is coming from multiple earth grounds. Okay. As far as possible, measurement signal circuits are actually isolated from Earth. However, a leakage path often exists between your measurement circuit signals wire and Earth. Okay, sometimes, particularly when your system, your cable system, sometimes there is some leakages, and these leakages will go to the Earth. Okay, so this if in your system, if your measurement system is only that things is the only measurement is the only one, or is the only system that connected to Earth, there is no problem. However, the problem is that is not the only component that connected to the Earth. Okay, for example, when you have other machinery or equipment that carry a large current connected to the same earth plane, so your measurement circuit will be in trouble. Okay, this can cause the potentials to vary to different between different points on the earth plane. So in this situation, which is known as multiple earth, this can cause a series of mode noise voltage in your measurement circuit. Okay, understand? Okay, another source of measurement noise is noise that comes from tension, voltage tensions. Okay, for example, when motors and other electrical equipments suddenly switch on or off. For example, you switch on your lamp or you switch on your fan, there is a large change of power consumption suddenly occurs in your electricity power supply. Okay, so this will cause an voltage tension or spikes in your measurement circuits. Okay, as you can see here, in traditional, when you watching your televisions, in the early in current television in LED, in nowadays television already have noise reduction on the tension, but in the old televisions, old generations of television, when you watching your television, when others of your family members switch on the fan or something, it will interrupt your television image. The interrupt of your image is due to the voltage tensions. I do not know whether you not uh, experience these things, but during my childhood, I usually experience this kind of things, and it is explained by these voltage tensions. So this noise voltage is a large magnitude, but is very short in time duration. It's only happens only less than a seconds or 1 seconds. Okay, so but it has a large value of voltage disturbed in your signals. Okay, so this noise we call as voltage tension. Okay, another source of measurement noise in your measurement instrument system, we have the thermoelectric potential voltage noise. Okay, so whenever metals of two different type are connected together, a thermoelectrical potentials is generated according to the temperature point. For example, if you have lead and copper as a wire, and then at the end of your point having a different temperature that join together, it will generate a thermoelectrical potential. It will give you a thermoelectric potentials. Okay, at one end having a high temperature, and at the other end point having low temperature, it will cause you different in potential, thermoelectric. This we call as thermoelectric. But this thermoelectric potential is very low. It only give you a few millivolts in your systems. So this noise is very low, and it only causes when you have two type of different metals. If you have copper wire and copper wire, there is no thermoelectrical potential. But if you have two type of metal different, then this thermoelectric potential noise will happen. Okay, so two condition, two different metals, and there is an temperature different. Okay, to make it happen. Okay, and then what we have here is another source of measurement is called as short noise. Okay, what is short noise? Short noise is occurs in transistors in semiconductor devices such as transistors, integrated circuit. Okay, so short noise in electronic devices result from unavoidable random statistical fluctuation of your electron. Okay, so electron emits fluctuates. Okay, although if you see in transistors, okay, although it giving you a DC current of 0.3 ampere, but if you zoom in, it's actually fluctuate. Okay, if your electronic components, okay, if you see here, okay, this is due to the random fluctuation in the rate of your carriers in the semiconductor device. So the random emission of electron that across of its junction will giving you some noise, will fluctuate noise in your system. Okay, so this is another example. This is another source of measurement noise. Okay, so another example of measurement noise is electrochemical potentials. So electrochemical potentials comes from measurement system that due to electrochemical actions. Okay, for example, if you have a poorly soldered joints, okay, so there are a common source. Okay, this will give you some leakages or oxidations will go through your systems. So it will giving you some noise to your measurement system. Okay. So how do we reduce noise in our system? So prevention is always better than cure. Okay, we always hear this proverb. Okay, so prevention is better than cure. So we already understand the source of noise. Okay, so and much can be done to reduce the level of measurement noise by taking appropriate steps when designing the measurement system. So some noise can be avoidable. Okay, so the aim when we design measurement system is always to reduce such induced noise voltage level as far as possible. Okay, so but it is usually not possible to eliminate all the noise, but at least we can eliminate certain noise that will be good enough. Okay, the thing is we need to prepare our measurement system that can be avoid some certain of noise, and for example the external noise that still remain, there is no choice. Okay, so there are some suggestions there are some techniques for the reducing the noise. Okay, so there is when designing a wire system, we need to take care of the position or the locations of your wire signals. And then second thing is the grounding and earthing. And then the third thing, we can implement shielding to your signal wire. And also we have other techniques like filter and so on. Okay, in another methods of implementation. Okay, so location and designing wires. Okay, as we discussed in previous slides. Okay, we have both inductance and capacitance coupling is due to signal wires and other cables are very near to each others. Okay, so this this inductive capacitance between the signal wires are inversely proportional to the square of the distance, okay, between between these wires and the cables. So noise that due to this inductive and capacitive coupling can be minimized by ensuring that the signal wires are positioned as far as away. So we can place your wire by having as far as possible to reduce the noise that coming from inductive and capacitive coupling. Okay, so a suggestion, a minimum separation of 0.3 meter is essential. So, and at least 1 meter is preferable. Okay, so noise due to this inductive coupling is also substantially reduced if each pair of the signal wire is twisted. Okay, if we have no choice to get near, so another option is twisted together along its length. So this design is known as twisted pair and is as shown in this figure. Okay, so although this twisted is very near to each other, it also will create this in coupling voltage noise. But okay, when we have this twisted pair at the first loop, okay, wire A will have V1 that is less than V2, and then in wire B you have V2 that is larger than V1, and then at the second loop now wire A have V2 and then wire B will have V1. So it will cancel each other when we have a design of a twisted pair. At least it will have effect, lower effect on the noise that coming from outside. Okay, for example, inductive noise or capacitive noise. Okay, if this noise source is a conductor that no electric current is flowing, then it will become inductive noise. So inductive noise will be lessened if you have a twisted wire or conductor. It will have a low noise voltage in the capacitive coupling. Okay. So another technique for reducing the noise is you need to take care of the grounding earth. Okay. So earthing is very important. Noise due to multiple earths can be avoided by good earthing practice. Okay. So in particular, this means keeping earth for signal wires and earth for high current equipment, we separate it. Okay. For example, if you have some high voltage current equipment, will have a separate grounding earth, and then a low power, low signal voltage will have another separate earth. Okay, so in this recommended practice is to have an as completely isolated earth circuit. For example, here we have four kind of isolated earthing grounding. Okay, we have power earth, logic earth, analog earth, and safety earth. Okay, for power earth, it provides a path for a fault current due to power faults. Okay, so this is connected to the power earth. And then for logic earth, provide for common line for all your logical circuit potentials. Okay, so because your circuit potential is between 0 to 5 volts, so we create a specific earth for your logic devices. Okay, because the high voltage for this one only 5 volts. Okay, and then we have analog earth or analog grounds. Okay, so this one provides a common reference for all analog signals. Okay, this will be, if you have another a special ground for analog earth, it will be very useful, as it will also will be a common reference for your analog signals. And then number 4 is safety earth. Okay, so this safety earth is connected to all metal parts of equipment to protect personnel. Okay, for your personal safety. Okay, for example, if some things happen and high voltage leakages, okay, so all the metal parts safety earth goes to safety earth. Okay, it somehow will protect you from safety from high voltage leakages when you are using some equipments. Okay. Another method for reducing noise is shielding. Using shielding in your wiring system. Okay, so what is shielding? Okay, shielding consists of an enclosed signal wire that is in the middle, this one. Okay, and then in the outer part of it as a metal shield that is isolated from the signal wires. Okay, for example, your this usually we have in your astro wires. Okay, so usually in astro wire do have big apa ni this kind of shielding lah. Okay, so this braided shield is in the outer space of your wire, and then at the core is the center conductor. Okay, so the signals is transmitted in the core wires. Okay, so please bear in mind that only one point is grounded shield, and then this shield that is connected to ground will terminate the noise from the electrical field, and then your inner conductor will be transmitting a very good signal. Okay, so a shield that consisting a braided metal will reduce 85% of noise due to the capacitive coupling. Okay, so the wires inside, such as shields, are normally formed. Okay, this one inside also, you can see some of the core wire also form a twisted pair. Again, to improve the protections against the induced noise due to the nearby electromagnetic fields. Okay, so the metal conduit is also sometimes used to provide shieldings from the capacitive coupling noise. Okay, so it is important. Okay, so if you see, this one is very popular used in your signal wires. Okay, shieldings. So another technique for reducing noise is by introducing the phase lock loop in your signal processing element to clean up the noise that giving you the poor output signals. Okay, for example, the usage of lock-in amplifier, when your input signals is already interrupted by the noise. Okay, so lock-in amplifier is extracted varying this one by referring the reference signals. Okay, so like lock-in amplifier, we reduce noise by comparing with the reference signals. So the output signals have a clean signals amplitude phase. Okay, so this is another techniques of reducing noise. Okay, so it's actually lock-in amplifier is actually another method of signal we call as a signal processing. Okay, so that's all for today lecture regarding the noise. Okay, so as a summary, you should by now you should understand what is noise. Okay, in previous chapter we already discussed the error in your measurements. Okay, in your measurement system, in the instruments, when you decide to do measurement using your instrument, it will have some error. Okay, when you having some signal transmissions and continuous measurement of signals, these signals do have carry noise. Okay, so we need to understand what is the sources of noise. Okay, there is some internal and externals. So by knowing that sources of noise, we can have the prevention of noise by applying the preventions to reduce the noise. Okay, so there, as we discussed, there are several methods for reducing noise. Okay, I hopeful that you understand my lecture, and then if you have any questions, you can ask me in the discussion room in the ULearn, or you can WhatsApp me directly and we will have discuss if you have another further discussion. Okay, thank you. I hope you after you listen this, please remember to record your attendance in the ULearn and do the quiz by the allocated time. Okay, thank you. See you in next session.